Good morning, everyone. I'm Steve Cantrell. I'm the chair of the mathematics department here at the university. I think I spoke to everyone here this morning, but it's my pleasure to welcome you all to Miami. Some of you are old-time friends who have been here many times, so welcome back. Many of you, I think, are here for the first time. Welcome. I want to make a particular welcome to Dr. Carolina Araujo, who will be giving the Frontier lectures tomorrow and Wednesday. This is a third in a new series that we're having, so we're very pleased that she's here to do that. I hope you all have a very good time here in Miami. I think you're going to have nice weather all week, so this is good. The last week that I was here, week before last, it wasn't so great here, but it looks to be very good now. So thank you very much, and I'd like to, my pleasure to introduce Felicia to give welcomes from our sister institute. Sophia.
Thank you. Dear colleagues, it's a great pleasure and an honor for me to say a few words at the opening of this conference. And on behalf of the International Center in Mathematical Sciences in Sofia, I'm actually the deputy director of this center. And our collaboration with INSA Miami began actually with the establishment of this center in Sofia, which was in 2020. And the center was established with the great enthusiasm of Professor Julian Revalski, who is the president of the Bulgarian Academy of Sciences. Also, Bogovet Sendov, who was the first director of the center, with the great enthusiasm of Ludmil Katsarkov, and also with the support of Philip Griffiths, Stephen Cantrell, Mina Teicher, and Yuri Chinkel. We started some joint initiatives, and one of the joint events is this conference we are opening today. The first event was the lectures of Professor Stephen Cantrell and Mina Teicher in Sofia in June 2021, followed by the inaugural conference of the center in June 2022, and by a conference on geometry and physics in Sunny Beach in July 2022. And the next event we are planning together is a joint event of the two institutions. It's a conference in August, again in Bulgaria, which is on a topic very close to the topic of the conference we are starting today. We also have another joint initiative, the two centers, the center in Miami and the center in Sofia. And this is the joint postdoctoral program, which started with a 2-year postdoctoral fellowship in July 2021. And up to now, we have 8 postdoctoral students, which are joint postdoctoral students of the two institutes. So one of them is here, Rodolfo. And one of them, Rene Boro, will join the academic staff of the University of Miami, as far as I know, in July 2023. So this is another joint initiative of the two centers. And finally, I would like to say that we are very thankful to the Simons Foundation, who gave us a grant that supports the center and allows us to organize all these joint activities. And we are also very thankful to the administration, and especially to the provost, Jeffrey, I don't know exactly the pronunciation of his family name.
Well,
okay, thank you. And also to the dean, Leonardis Bachas. Thank you. So, welcome to this conference. We open the conference with the first talk of Tony Pantev. It's a pleasure for me to introduce to you Tony Pantev, a professor from the University in Pennsylvania. He is very closely related to the activities of both IMSA and ICMS Sofia. Tony, you have the floor.
Thank you. Okay, hopefully it definitely works. As always, it's a great pleasure to be here. And the topic of this meeting is extremely interesting and really venturing into new ideas and new questions that I hope will really invigorate the subject, which has been around for a while, but somehow has been a little bit detached from the mainstream, especially of algebraic geometry. So I hope what we discuss here this week will actually reintroduce the subject back into the mainstream of algebraic geometry. Okay, so I'm going to talk about generalized complex branes and the way one can interpret them as geometric structures in a slightly touched up version of symplectic geometry, which is very well suited for algebraic considerations, which is shifted symplectic geometry. And so this is part of a joint work with Safronov and B. And I'll also mention several very interesting and relevant results that were recently proven by APG. And as I said, what I'm going to talk about is I'm going to give a symplectic interpretation of generalized complex geometry. And as you'll see, this interpretation actually leads to a new concept, a new idea of trying to understand in algebraic geometry complex structures by introducing some homotopical ambiguity to them. So I'm going to talk about homotopy complex structures. Hopefully, I'll get to that. And a new one, the derived. And where this is leading, and I'll mention it, but I'm not really going to talk about that because this is still very much in progress, mostly in the work of B. This is all leading to actually understanding what are the natural homomorphisms, which are the natural mass between generalized complex branes. So this is really leading towards a category, constructing a category, PC branes. But directly without guessing can be some natural, very, very geometric way. As we do it in algebra. Okay, so let me start with a very brief review of generalized complex geometry in the shape it will appear in my story, and we'll hear many other talks about generalized complex and generalized scalar geometry this week that hopefully will fill in the gaps. This is going to be very fast as well. So generalized complex geometry, it was discovered by teaching in 2004 and fully developed by Kaehler in 2011, and then many other people contributed with in a very substantial way. And it's been a very rich and actively developed subject for many years since then. Somehow the takeaway from a bird's view what this is it's a new differential geometric structure that one can put on a C-infinity manifold. And it actually solves two problems, serves two purposes, at least partially solves two problems. One is that it continuously interpolates between complex and symplectic geometry. Which is something quite remarkable, predicted by physics, but quite unnatural from the perspective of higher complex of symplectic geometry. And the second thing is it interpolates. If you don't know what this word means, you can ignore it because I'm not going to talk about this aspect, even though it's very interesting. It interpolates between topological twists. Quantum field theories. With two common to supersymmetry. Again, it is. So it's actually useful, again, for the discussion we want to focus on. Just want to talk a little bit about the sort of historical origins or what prompted this this development. And I mean, it has many roots, in particular, deep roots in bidimensional geometry. I think Gil is going to talk about that, right? But the root I want to focus on is actually coming from algebraic geometry, and so precursor or origin. This is coming from the coisotropic branes of Kapustin and all. And let me say a few words about that. So this happened a year before teaching started developing this. So what Kapustin and all was studying, they were studying these very special algebraic cycles. So these guys are mirrors in the sense of quantum mirror symmetry, near-electric special cycles. Algebraic varieties, in fact, they studied them on billion varieties. But they make sense on the algebraic variety. I mean, the coisotropic branes make sense on the mirror of any algebraic variety, or any Calabi-Yau or any projective variety. But Kapustin and all studied them on billion varieties. So, if you look at cyclopedia at some point, you know that if you take a projective variety and you look at cohomology classes, even degree cohomology classes, they are realized by algebraic cycles only if they have a Hodge type PP. So if it's a cohomology class of codimension P, then it has to be realized by a Hodge class of type PP in order for it to come from an algebraic cycle. Hodge conjecture says that rationally it also can really from algebraic cycles. But the classes of type PP, they are not well behaved under deformations. So if you start with a variety and you start moving it around, and you start with a homology class of type PP, it will not necessarily stay of type PP. In fact, it can disappear in the nearby deformation. And so there are these special classes of Koch type PP on a given algebraic variety, which actually stop being type PP once you deform slightly the variety. So those are the inoculation classes, and very often they realize by cycle. And this happens with billion varieties. And when it happens, you can wonder what the symplectic counterpart. So mirror symmetry is this physical duality that converts complex geometry into symplectic geometry with some other manifold. And normally algebraic cycles or supports of computed shifts in an algebraic variety under this conversion go to these invariants of the symplectic structure in the mirror, which are Lagrangian submanifolds equipped with some bundles with flat connections, maybe slightly more data. But these special types, it's very simple to write down examples where for an abelian variety, generic in its moduli, the Koch classes, when you mirror them on the other side, they give you all the classes of all possible Lagrangians. And then you get these extra classes that do not appear generically. So where do they sit inside the mirror? And Topuskin and Orlov actually analyzed this problem and gave an answer, a very precise answer. Right. So another way to stage this is to say if you have a symplectic manifold, C infinity symplectic manifold, you would like to have some natural linear theories, natural theory of sheaves adapted to the symplectic structure, which captures the geometry. So what are the natural sheaves? Capturing moment. That's the question. And so it's a question which is supposedly illuminated by mirror symmetry and by this type of considerations. And so there is an answer which says that the symplectic sheaf so this is in some classical limit. I mean, there is a much more refined notion of this, which is really a truly very symplectic structure. But this is some cruder version of it, which is happening in what's called the large volume limit. So this is what I said. It's a triple. Y psi and nabla, where is it visible or difficult structure? So Y is a Lagrangian submanifold. Psi is a complex line bundle on Y. Say, since I fix it matrix, I'm going to say U1 bundle on Y. And nabla is the flat connection. So that's the yeah, maybe I should say I'll say complex line bundle, and then I'll say the connection is condition. Okay, so this was somehow the original answer to what the linear content of symplectic manifold should be, and this is limiting regime. But it doesn't account for these jumps in the mirror complex geometry. And so this is what I would say the Kaehler's answer. The Kaehler's answer is much more delicate, in fact, because he really described this not in the limit, but described them as an actual invariance where this notion is actually deformed by counting pseudo-homomorphic disks is by the symplectic manifold with boundaries of one. And it is really essentially complete invariant. So the collection of those guys is an essentially completely invariant of the symplectic structure. But in the limit, it still gives you some information. So the answer by the Pustin and Orlov expanded slightly this picture, and it said that the symplectic shift is a triple again, where y inside x is now not Lagrangian but isotropic. Psi again is a complex fine bundle. Now is a connection on psi emission. But now, because we're on a isotropic submanifold, we don't require that the connection is flat. We only require it to be flat. Let's say it has curvature as nabla, and if you normalize the curvature, so if you say f is 1 over 2 pi I the curvature of the connection to make it integral periods. But it's a twofold, right? Because it's curvature of the connection in the line bundle. This twofold so satisfies the condition, which is the analog of the integrability condition for the Lagrangian guys. So f is 0 on the list of the new foliation of the isotropic manifold. So the new foliation, we call it IY, This is just the kernel of the symplectic form pulled back to Y. And view as a form, and view it as a map from the tangent bundle of Y to the cotangent of Y. And furthermore, so it descends to the Lie space, and on any slice to the list of this foliation. So the quotient of our coitropic guy by the new foliation is formed. Never remember what the direction is. Which one is first? Okay. So this slice of the list is formed satisfied that if you take omega multiplied by f and square it, this is an orthogonal. And so omega and f both come from the Lie space, and on the Lie space, their composition gives you an almost complex. And in fact, the Kostianov check that this already implies that this almost complex structure is integrable. They also check that if you take the form, which one? If you take a complex form in which f is the real part and omega is the imaginary part on the Lie space, this form is homomorphic. Symplectic. With respect to this integral. And it's completely elementary to check that if the coitropic manifold happens to be Lagrangian, then this equals this. And so this coitropic branes, they're somehow an amalgam complex geometry along the Lie space of the coitropic manifold and symplectic geometry along the leaves. Right, so the leaves are actually isotropic, and the complex geometry is happening from the Lie space. So this is actually a precise feature. Maybe it's useful to make this remark, even though it's kind of obvious. But if you think about why, so say script y is the quotient of y by this foliation, whatever that means, then you can look you can think about why has been fired over the quotient space by the leads. And of course, the population is the relative tangent among the fibers. So you have a family of manifolds over something which is homomorphic symplectic. And what you can do is you can pass to the family of relative tangent. So the question, the relative tangent bundle is sidewise, and the relative tangent bundle is the dual. Right? So this is just the total space of IY dual. Splitting over Y, it's nothing over Y. But what's more important is that, so this guy now 5x over Y. So now we're going to figure symplectic manifolds over Y to tangent bundles. And this guy is some kind of a two-bar negative straightening of Y inside X. So it's locally isomorphic to a neighborhood of Y inside X. Defined symplectic. By the Einstein that would do it. So what the brain condition of the Pustin says is that it says that, okay, we started with some manifold which a priori was just symplectic, but we have this extra piece of datum B, and that extra piece of datum actually puts a structure on that manifold. It really becomes the product of the homomorphic symplectic one by an ordinary symplectic one, and the Y is Lagrangian in each phi. It is the zero section tangent. So it really realizes the symplectic manifold Y as a family of tangent bundles over this homomorphic symplectic guy, and the coisotropic guy is just a family of zero section. Okay, so why am I talking about this? Because one thing that the Pustin and Orlov didn't analyze, or analyze in a very minimal way, is to understand what are the natural maps. I mean, on the mirror side, we have always natural maps between, say, structure shapes that multiply subvarieties. And these guys are mirrors. The coherent shapes, the order multiply subvarieties, structure shapes, multiply subvarieties. So we know what the forms are on the mirror side, and what are the forms on this side. And yeah, so this is the puzzle. And once you understand what the mass are in the limit, how we quantize them by using frequency with this homomorphic mass from this. So what are the mass and how do we quantize spaces of mass if we know what the answer is by liquidity. Okay, so there are a couple of answers to this puzzle, but they're both either in examples or partial. So the first one is due to Bozoit and Smith. I think 2010. And they analyzed one particular example, which is the example of the square torus. So take the billion surface, which is given by the square ones in C2. So it does have not a special branes because it's a billion surface with complex multiplication. So the graph of the complex multiplication is not a special, it doesn't default in the moduli of billion varieties. So the mirrors the Newton-Lefschetz spatial branes. Isn't this a product of the It's a product of the square entity. It's the square of the square entity. So it doesn't it's moduli, but the brane, cost plus, it doesn't stay. But the square entity has multiplication by total unity, and because it's a square entity, there's also the diagonal. So these are two cost classes that do not depend. They disappear. So the mirrors of the Newton-Lefschetz special branes are actually appear in the Karoubi closure. Of the Lagrangian things. Of the Foucault category. So if you take the large monolinear Foucault category, which is described by Lagrangians, deform it by genus zero pointed curves with the boundaries of the Lagrangians, and you get an infinity category or differential credit category, which is not idempotent complete. And the derived category potentially so many projective varieties is idempotent complete. So the naively constructed Foucault category has no chance to be mirror of anything coming from a derived variety. But you can idempotent completely, right? So any category has a canonical idempotent completion, which is a universal one. So if you take idempotent completion, then it has a chance to be mirror to the category in a sheet constantly. And what Bozoit and Smith proved is they proved that these two cycles that I just described, complex multiplication one and the diagonal, actually do appear in the Karoubi closure. And they identify which options they are. So somehow the answer to this puzzle is that, well, we started with something that really doesn't describe all objects in the category, but somehow generates the category, because we can start with all those guys which are Lagrangian, produce a category, and then at the bottom completely we'll add some objects. And then the new objects, the completion that we are describing, split closure, it should be the correct thing. And so the answer is that these coisotropic guys will realize objects in that idempotent completion. There's the expectation, of course, the only case in which I know is actually checked is this case. Another answer, which is what started this project, is given by theorem 3B. And what he did is he actually understood that again for chloride, there is a double which converts these isotropic branes to actual Lagrangian branes and converts them in a way that's compatible with Fox. So given a symplectic torus, so say T is a symplectic torus for vector space modulo lattice and a form, which is translation invariant. You can, so this is the symplectic torus. You can look at the view symplectic torus. I mean, you know, it's the thing of smart. So there is a dual torus. And now you can look at the product. So this has a bifield. So it has a couple of structures. One is a bifield. So it's a two-form of the dual torus, which is given by the identity inside video tensor B. I'm going to call it B. And then there is a complex structure, which is given by B inverse times omega plus minus omega inverse. It's a complex structure. It's actually an integrable complex. And what he deduced was that any isotropic brane Y psi nabla gives rise in a very explicit way, which I'm not going to write, to a Lagrangian brane. Let's say Y underline psi underline on this double torus. Let's call this guy T. And but it's a Lagrangian brane on T underline with the complexified symplectic structure. Specified by the difference. And in fact, this Lagrangian brane is homomorphic. The J data. And then the compatibility of cones. So if you take a cone between Y and Y prime in the Kaehler category of the original torus, this is actually equal to the Floyd complex between Y underlined and Y prime underlined, slightly modified. So you have to do two things. First, you have to take the zero dot Floyd complex. So these are homomorphic Lagrangians. You can write four chains, from between them in the Dolbeau realization for the complex structure on the double torus. And this thing is actually acted upon by the dual complex in order to take the fixed point. So this actually gives you a factor from the usual Kaehler category. This is for when Y and Y prime are actually Lagrange. If you factor from the usual Kaehler category of torus, the straightened one, the one corresponding to translation into the flat Lagrangians, to this Dolbeau homomorphic Kaehler category of the double torus with the given detail. And then you can, and because every isotopic brane is also realized as a Lagrangian, homomorphic Lagrangian in the double torus, you can just take this as the definition of the quadratic. So that gives an answer to the puzzle. And in fact, it's fully faithful embedded from this flat Kaehler category to the Kaehler category of double torus. So the only drawback of such important cross answers is that I mean they're quite compelling and interesting. The drawback is that, well, one drawback is that it's not clear how to compare them. The other drawback is that they're both about tori and about flat branes of tori. But this, by the way, you can just quite special samples are flat in the torus. Okay, so what we would like to do is to take away some idea from this picture, especially from this picture, and try to understand how to write these branes on any symplectic manifold with no condition on the manifold. Again, as some natural Lagrangian branes somewhere is a double version of our symplectic manifold. And of course, you know, this is not available anymore. Okay, so this takes us to the DC branes. And so this is as I said, this was proposed by Hitchin and then fully developed by Gualtieri in the form that I'm going to discuss it. And it's some way to actually universalize, understand this exotic Kapusky normal sheaves. But in fact, it may also understand them in some more general and more flexible context. And so what this does, it starts with the C-infinity manifold and introduces this structure. So there are many different ways and levels of precision with which you can talk about those. I'm going to talk about them in the most pedestrian way, which is pretty close to the best way to talk about them. I mean, there is slightly more invariant way to talk about GC structure than GC branes in terms of Courant algebra, but I'm just for the purposes of the talk, I'm not going to use that, even though it's better in some sense, especially for understanding statements and proofs. So a GC structure on X, it's a pair J and H, and J, it's an endomorphism of the sum of the tangent bundle and the tangent bundle. And it is almost complex structure of that sum, squares and minus 1. H, it's a triform on X, which is closed. And there is one more condition, which is an integrability condition, which says that J is integrable with respect to the Courant bracket on the tangent plus the tangent bundles. And the Courant bracket, this is the H with the Courant bracket, and the Courant bracket is given by so if you have a tangent vector plus a form, another tangent vector plus another form, the bracket of that is the bracket of vector fields plus the lead derivative with respect to the first vector field of the second form minus the contraction of the second vector field with the derivative of the second form, and then we contract H with the two vector fields. Oh, I got the signs. And so integral means that if you take the eigenspace corresponding to the eigenvalue I, that gives you a complex subbundle in the sum of T and T hat, it's preserved by this bracket. And the GC brane, it's something very similar to what we've been seeing. So it's again a submanifold, a complex line bundle, a two-form, and a connection. And Y is a submanifold. Conclusion. This form is a primitive of the tree form when we pull it to Y. And well, that's there is the quantized tangent bundle. The GC tangent bundle Y which is right. So the GC tangent bundle of Y, so it depends on Y and length. So it's all elements U alpha, which are tangent vectors to Y, plus sections in the cotangent bundle of X expected to Y. And there is a condition, and the condition is that the pullback of alpha restricted as a form is equal to the contraction of N. Is that clear? And the condition, so the GC brane condition says that that this generalized tangent bundle is preserved by the GC structure acting on EX plus E X dual restricted to 1. I mean, this guy is a sub bundle here, so this generalized bundle is a sub bundle there, you want it to be preserved by. And then automatically follows that the I space for J on the complexification of this guy is closed under the Courant.
You might also want Y to be coincid.
Did I not say that? Well, coisotropic for what?
The process.
But that follows from J preserving, right? Yeah, and so this implies that I space of J on this generalized bundle, tangent bundle, and so C is closed from that direction. And so it gives you the real algebraic, complex real algebraic on Y, and the condition of the connection is that so I didn't say what nabla is. So psi is a complex line bundle. So this is L, complex real algebraic on Y. And the size of complex line bundle now is actually a connection on psi, make psi a model over that. So now is a connection which is well, so it just said that now psi is a model. How much time do I have? Okay. An hour or 50 minutes, because I'm already at 55 minutes.
Yeah, 1 hour.
1 hour. Okay, so I'm going to say one more thing and then we'll stop. And so the two examples are in the battery stack. Okay, thank you. Just spend 2 minutes talking loudly.
Here's another one.
Yeah, just for the next one. Yeah, maybe 3 examples. So if omega is a symplectic structure, on X, then 0 omega inverse omega 0 and the 0 3 form give you a GC structure. If and maybe I should say what you're saying. In this case, GC branes are automatically coisotropic. For the symplectic stuff. If
Is that 0 there? For
this one,
no, this is H.
this is H. H is 0.
For F, for the brain. Define a brain.
No, for the brain actually not be 0. It just needs to be close. Yeah, it just needs to be close. Yeah. And if I is just a complex structure, on X, then I dual 0 0 and 0 is a GC structure. And at least homomorphic line bundles on complex subvarieties submanifolds give GC plane. They're slightly more GC plane, at least those are. And the third one, which is also interesting and relevant, is that if you have I complex structure and P homomorphic Poisson structure,
then I check 0 and P in the upper right corner, and 0 flux is a GC structure plus homomorphic line bundles on coisotropic homomorphic submanifolds are GC branes if they satisfy an integrability, quantizability condition. So the homomorphic Poisson structure gives you a deformation quantization of the complex manifold. And you can ask, when is a homomorphic line bundle on a complex submanifold unobstructed in the deformation quantization? So there is a first order quantizability condition, and if it satisfies it, then it's okay. Okay, so I'm going to stop, and then we'll talk about the shifted symplectic geometry interpretation of all this in the next hour.